So again, last week, the major theme was dilutions. And dilutions was just a mechanism for doing one of two things. Either we took a serum, which was a medication, liquid, powder, or whatever, and we dissolved it into a solution. So it was a ratio of serum to total solution. So let's say we had a 1 in 8 dilution, then that would have meant 1 part serum for every 8 parts total solution. Or the other possibility, rather than a serum, a pure medication to a total solution, we might have diluted an existing solution. So we had the concentrate to total solution. And both of them gave us significant consequences as far as constituting medications. For the dilution, the 1 in 8 dilution of serum into total solution, let's say we want to know how much saline to mix with 40 milliliters of serum. Well, we have that 1 in 8 dilution, but remember that 1 in 8 dilution, as we noted up here, is serum to total solution. We're looking at serum, we have the 40 serum, but we don't care about total solution, we want the saline. So that ratio of serum to saline, there's still 1 part of serum, but if there's 8 total parts and 1 of them serum, there's 7 parts that are saline. We have the 40 milliliters of our serum, and we cross multiply and divide. 7 times 40 divided by 1 gave us 200 milliliters of saline, which we would combine with it. Our concentrate, using this type of a dilution, was actually much more active, had a few more applications. One of those applications would be, let's say, 40 milliliters of 28% solution is diluted with 120 milliliters of saline. Find the new concentration. Well, there's a couple of ways we could go about doing this. We could either find what the dilution was. That dilution, of course, would be the concentrate over the total solution. We had 40 milliliters of concentrate over 40 plus 120 total solution. So that gave us 40 over 160, which reduces to a 1 in 4 dilution. Now then, that is our ratio of concentrations. 28%, of course, is going to be the larger concentration because we're diluting it down. We cross multiply and divide. 1 times 28 divided by 4, it goes to a 7% concentration. The other option we could have done there is we could have used that concentration adjustment formula. The C1V1 equals C2V2. And we had 40 milliliters of a 28% solution. That's V1 and C1 right there. So 28%, we're just going to leave it as 28 times 40 milliliters equals, we don't know what that new concentration is, but the new volume is the 40 plus 120. And if we solve that equation, we're going to come up with the exact same thing. The new concentration is 7%. We also looked at some of our how the concentrations were calculated on Friday, And the things to remember there is when we have a weight and weight solution, it is additive. Weights are always conserved. So if we want to know how much NS to add to, let's just go 30 milligrams of lidocaine to create a 15% solution. We can actually calculate that. We can do the 15%. Now again, the 15% is the lidocaine, the medication, the serum, the total. So when we plug this in, the 30 milligrams is the lidocaine. We'll cross multiply and divide. 100 times 30 divided by 15 is 200 milligrams. That 200 milligrams is the total solution, but we can simply subtract 200 minus 30 to get 170 milligrams of saline that would be added. That's the advantage of using the weight and weight solution. If we had volume and volume solution, remember, the key there was that those are not necessarily additive. Sometimes you add two volumes and the total is less than what you would get if you just added the numbers for the volumes together. So be careful with those. Yep. This one? Okay. So now if this is a volume and volume solution, let's say we want to know how much saline to add to 60 milliliters of isopropyl alcohol to create a 20% volume and volume solution. Well, here the 20%, 20 over 100, once again, the 20 represents the serum, in this case the alcohol, and the 100 is the total volume. We put in the 60 milliliters for our alcohol and we cross multiply and divide. 100 times 60 divided by 20 is 300 milliliters. The total solution is 300 milliliters. We'd have to be careful here though, because if we subtract 300 milliliters total minus 60 milliliters of alcohol, we get 240 milliliters. But that's not necessarily telling us how much saline we need. We need at least 240 milliliters of saline. Because sometimes when you combine two fluids, and alcohol is one of them, that when you combine alcohol with water, the volumes don't necessarily add up. If you add 60 milliliters of alcohol to 240 milliliters of water, you might end up with something like 290 milliliters. They don't necessarily add up. That's what we discussed last time about the particles of the solute hiding in those particles of the solvent or the water. Just like salt disappears in the water in salt water. And then the final was the weight and volume solution. Now, of course, you probably remember the weight is always really a mass. We just call it a weight and volume. But anyway, a weight and volume solution. And the big thing to remember there is the weight is always in grams, while the volume is still in milliliters, which it seems counterintuitive. You would think it would be milligrams and milliliters, but it's not. Remember, 1 gram is defined to be the mass of 1 milliliter of water. And most of our medications are about 1 milliliter. Or sorry, are close to the consistency of water, I should say. So anyway, I want to now take a look. The first thing we want to look at today is I want to look at page 150 in your book. Uh, just a couple of things I want to note about it. We aren't going to actually lecture on these, and we're not going to specifically test you on these, but this contains several of our medical abbreviations. Certain things like, IV stands for intravenously, or IM stands for intermuscularly. One that we've already talked about, GTT stands for drop or drops. PO, orally, not necessarily a big one for us. We're not really terribly concerned about how it's administered, but ones that are a big concern mathematically for us are Q4H, Q4H or Q6H, or TID. The Q4H means every, or Q6H means every 6 hours. Q4H is every 4 hours. Q8H, of course, then would mean every 4 or every 8 hours, which ends up being equivalent to our TID. TID means 3 times daily, which of course is equivalent to every 8 hours. The reason these are important to us, like I said, I'm not going to specifically test you on the abbreviations, but we may need to know them because we might look at a doctor's order where the doctor might order 60 milligrams Q6H, and the label, the recommended dose of the medication might say up to, well, let's say up to 40 milligrams 3 times a day. So we need to be able to compare those to see if those are equivalent. And it ends up that they are not. There's going to be some issues with it. But we need to be able to make those mathematical conversions between something that's every 6 hours, which would be 4 times a day, to something that's 3 times a day. And we'll look at those as we go along. So that's something, that page 150 in your book might be something to bookmark. Put a scrap of paper in there or something so you can refer to that rather quickly. Because as we do the dosage calculations, that is going to be an important page for us. The next thing we want to do today is we want to look at syringes. Throughout every program I teach for, whether it's construction or manufacturing or whatever, it seems common that people struggle a little bit with reading scales. So we're going to take a little time here to deal with syringes and scales on syringes. Now, what I have here are blank syringes. When we're looking at filling a syringe or reading a syringe even, the first thing we need to do is figure out what each division is or stands for on that syringe. Kind of like any scale we read, that's the first thing we really need to be able to do. So let's say that this is labeled in milliliters. This is 1 and 2. Now, a lot of times the beginning of the syringe is a little hard to read. Mine are kind of square cut, but often they're kind of tapered like that. And so the first couple of marks might not even appear on the syringe because those are down in that tapered portion. So it can be awful hard to read. So a lot of times what we'll do is we'll go to the first labeled marking away from the end of the syringe. In this case, that's the 1 millimeter. And then we'll go to the next one, in this case, the 2. And to figure out what each marking stands for, we first of all look at that range, 1 millimeter to 2 millimeters. Well, we're going to subtract. 2 millimeters minus 1 millimeter milliliter, I should say 2 milliliters minus 1 milliliter is 1 milliliter total. So we have a volume of 1. Yep, go ahead. Okay, I'll have the recording posted by the middle of the day tomorrow for you. You bet. We'll see you later. So I've got 1 milliliter of range there from 1 to 2. We have, if we count, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20 divisions there. Now we could have counted that this is 5 and just said, hey, those are all the same, 5, 10, 15, 20 as well. So 1 milliliter divided by 20 divisions, that is 0.05 milliliters per division. So each marking on this syringe is 0.05 milliliters. So now, if we fill that syringe, let's say we fill it to right there. Notice it may not be perfect on the marking. I'm certainly not perfect there, but we read it to whatever the closest marking is. We know this was the 1 milliliter. Each of those being 1 or 0.05, what we can do is we can count up 1, 2, 3, 4, 5. And again, I'm going to go 10, 11, 12, 13. That's 13 divisions past the 1. So we multiply it out. 13 times 0.05 is 0.65. So that's 1 plus 0.65 or 1.65 milliliters. Now, some of you, as you get good at this, may learn shortcuts. You might be able to look at this and say, hey, that's right in the middle. That is 0.5 milliliters there. So then you can count up. 0.5, I would read it as 50 hundredths, 55, 60, 65. So you don't necessarily have to do out the math if you get good with the scales. Let's look at another one. So this next one down here, again, this is milliliters. We're gonna assume these are marked in milliliters unless otherwise stated. And let's say we have 1, 2, 3, 4 like that. I'm gonna go ahead and fill it up. I'm just gonna mark it on bottom so I don't cover up my numbers. So I'll mark it like that. So now our first step is to figure out what each division stands for again. Well, again, we're gonna go from here to here. That's 1 milliliter of range, the 2 minus 1. Then we're going to count our divisions. So we've got 1, 2, 3, 4, 5, 10. Times 2 would be 10. So that's 10 divisions covering that 1 milliliter range. 1 milliliter divided by 10 is 0.1 milliliters per division. So now we go here. Here's the first or the last labeled marking before the end here. That's 3 milliliters. We've got 1, 2, 3, 4 there. 4 times 0.1 is 0.4. We'll add that on to our 3 milliliters. That's 3.4 milliliters. Now again, many of you might get good at counting these out. So you may just look at this and say, hey, that's 3.1, 0.2, 0.3, 0.4, 3.4, counting them up. So we might have one labeled like this. So again, now let me go ahead and fill that up where I want it. We'll fill it like that. So again, we're going to go between labeled markings. Now it goes from 0.5 to 1. So 1 milliliter minus 0.5 milliliters is 0.5 milliliters. Between them, we have 1, 2, 3, 4, 5, 10, 15, 20. So divided by 20 marks, that is 0.025 milliliters per division, per mark. So now this one's a little bit more awkward to read. This is our last marked location, that's 0.5 milliliters. We have 5, 10, 11, 12, 13, 14 divisions times 0.025. Giving us 0.35 milliliters. So we combine 0.5 with 0.35, you get 0.85 milliliters is what that syringe is containing. Could go the other way. Could be labeled like this. So let me fill this one again. Oops, somebody make that a little bit. There. Not quite so off. But anyway, so for this one, again, we can take two labeled markings. We'll go from the 2 to the 4. That gives us a difference of 2 milliliters in that range. And the number of markings is just 1, 2, 3, 4, 5. So 2 milliliters divided by 5, that's 0.4 milliliters per division. So if we look at what we're filled to here, this is the last division that's labeled. That's 10. 1, 2 divisions. 2 times 0.4 is 0.8. Combining the 10 and the 0.8 is 10.8 milliliters. So you can see the key, and this is the key to reading any scale, whether it's a voltmeter, any sort of dial meter where you have an open dial rather than a digital display. The key is figuring out what the divisions stand for, what each marking is. And that's this calculation here, where we find the range between two marked points, then how many spaces, how many divisions are between there, and divide that out. Now, of course, I'm using a blank syringe worksheet here. So all these syringes are the same width. But if I compared this syringe here with, let's say, this one up here, let's just do these last two here. The big difference between these is not going to be just the markings on them, but it's going to be the size of the syringe. This one up here, since it goes from 0.5 to 1, only contains 1 milliliter of fluid total, is probably going to be a very thin syringe. This one down here, since it goes up to 18 milliliters total, in order to have that kind of volume, it's probably going to be a very wide syringe. It has to be wider so that every space can hold more fluid. Now, with that in mind, I'm going to actually flip back to our page here for a second. With that idea in mind of the size of the syringe, the width of the syringe corresponding to the scale, which syringe would be fatter or wider? In fact, let's do it this way. Which syringe is going to be which? One syringe goes from, our first marking is going to be labeled one, two, like that. And the other syringe is going to be labeled 2, 4, 6, 8, 10, like that. So if I label these syringes A and B, this first scale, does that match up with syringe A or syringe B? Well, each division is a smaller amount of medication. So that goes to the narrower syringe. That's going to go to syringe A. The second scale here, since each division is a larger amount of medication, each division here is actually 4/10 of a milliliter, where over here each division was actually only 5/100 of a milliliter. That scale is going to go with the wider syringe. With that in mind, we let our dosage determine which syringe we're going to use. So back to this worksheet here. Come on. So if I have a dosage that I need to administer 1.8 milliliters of medication. And I have two options. I have syringe A up here that is labeled like that, or syringe B, which is, oops, I got that off a little bit. There we go. Labeled like that. Which one do I want to use? Well, I want to use the syringe that is going to be the fullest. Oops, get back here. The reason I want to use the syringe that's going to be the fullest is that's most likely the narrower syringe. Up here, if I were to fill this to 1.8 milliliters, it's going to look something like that. That's all it would take. This one down here, 1.8 milliliters, is going to be something like that. Well, why is it good to have the fuller syringe? Well, this one up here is going to be wider. Oops. Let's go like that. If that plunger in that syringe is off by even a small amount, let's say that's exactly 1.8 right there, exactly where we want it to be. If we're off by even just a tiny amount to right here, like that, that little bit of difference, because it's a wider syringe, is a considerable amount of medication. But for the smaller one down here, since it's narrower, let's say 1.8 milliliters is right here. If that's off by just a tiny little distance, the same tiny little distance, that difference is going to be a lot less medication than what we would have in the wider syringe. Okay, so then the other side of it is rather than just reading syringes, knowing where to fill them. So let's say we need 4.7 milliliters of medication. And let's say this one up here is labeled 1, 2, 3, 4. This one down here, like this. Well, we look at this first one. Each division here, if we figure that out, is one milliliter between there, 10 divisions. So it's 0.1 milliliter per division. This one, from there to there, is still 1 milliliter, but there's only 5 divisions. That's 0.2 milliliters per division. If I need 4.7 milliliters, this is 4, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. 4.6 milliliters appears to be the capacity of this. Well, you might say, what if the plunger is on the very, very end there? We don't want to risk that plunger completely coming out of the end of the syringe because that's unsanitary. Once that plunger comes out, germs get in there and we can't use that syringe anymore. So we risk pulling that plunger out too far and then contaminating all the medication we've put in there. So even though this is a smaller syringe, it's too small. So this one down here is 0.2 per division. This is 4, 4.2, 4.4, 4.6, and 4.8. We would be between those two markings. So we would have to try to be careful to fill that up to about halfway between those markings. I didn't do a very good job there, but you guys get the idea. Oops, I didn't go far enough, in fact. Now, most of the time, hopefully we'd be able to find a syringe that's a little bit better that would give us a marking that's what we want. We don't like guessing between markings like that. So anyway, that's scales on syringes. Does anybody have questions on reading these scales? Okay. So then I want to go back to, so we're going to make that page go away. So kind of just a little bit to get us prepped then for the next class. Our next class, we are going to start doing dosage calculations. Well, one of the possibilities we have for dosage calculations is formulas. The problem I have with formulas is two things. One, you have to memorize them. And there are a lot of different formulas depending on what information you're given, a lot of different formulas that apply to our different dosage calculations. And two, sometimes they can be unclear or just not quite fit the situation. Let me give you some examples of our dosage calculation formulas. One of them is D over H times V equals A. Well, let's specify what each of these mean. D is the desired dose. I always think of D for doctor. That's what the doctor has ordered. H stands for the on-hand dose. That is the amount of medication, that the concentration of the medication that you have that you're going to be using. V is the vehicle. This is what I always think is the most confusing part of this. The vehicle is what carries the medication from the bottle or the vial into the patient. And A is the amount administered to the patient. Let's look at an example of this. Let's say the doctor orders 40 milligrams of a medication. We look at the bottle, the label on the bottle says that it is constituted at 25 milligrams per 4 milliliters. Well, to fit this into this formula, D is pretty obvious. That's always pretty obvious. That's the doctor's orders. 4 milligrams. H and V are the tricky parts. H and V both come off of the label, the bottle's label. And they're often given as a rate, and that's exactly what it is here. They're given as a rate, 25 milligrams per 4 milliliters. H always has to have the same units as the doctor's order. So the H, the on-hand dose here, is the 25 milligrams. Now we ask ourselves, what carries that 25 milligrams into the patient? Well, 4 milliliters of fluid is what carries that into the patient. The 4 milliliters is the vehicle that carries that on-hand dose of 25 milligrams into the patient. So now it's just a matter of calculating it out. 40 divided by 25 is 1.6? And then 1.6, notice the units cancel out, the milligrams cancel out, so this is unitless. 1.6 times 4 milliliters is going to give us 6.4 milliliters is going to be administered to that patient. Now, a slightly different example. Let's say a doctor orders 1,000 milligrams of, let's say, ibuprofen or some sort of painkiller. And the label on the bottle is 4 milligram tablets. So now here, the order again is obvious, 1,000 milligrams. The on-hand dose has to match the units of the doctor's orders. That's going to be the 400 milligrams. The vehicle that carries that on-hand dose into the patient is a tablet. You can think of that 400 milligram tablets as being 400 milligrams per tablet. So that's going to be one tablet that carries that dosage of 400 milligrams into the patient. So again, the units cancel out in our orders versus our on-hand dose. 1,000 divided by 400 is 2.5 times one tablet. So 2.5 times one tablet is 2.5 tablets. Now, something we'll talk about will be scored tablets. A scored tablet means it's marked so it can easily be broken in half or chopped in half. When we're dealing with tablets, we usually round to the nearest half of a tablet. That's something we'll have to get used to. Let's say we calculate that out. Let's say we calculate 3 1/3 tablets. What do we administer to the patient? Well, 3 1/3 is between 3 and 4, but 3.5 is in the middle there. 3 1/3 lies right in here, 3.33. That's closer to a 3.5 than it is to 3. So we would round that to 3.5 tablets. Now that formula isn't terrible, but when you throw in that there are other formulas that we have to use, for example, for IV flow rates, our most basic formula for IV flow rates is simply volume in milliliters over time in hours. That just gives you what that IV flow rate will be in milliliters per hour. But there are other forms, depending on how, if we're using an electronic infuser, you can set that as milliliters per hour, and the infuser figures everything else out as to what goes into the patient. But if you're not, if you actually have to set the drip on a bag, you need to know what the drip rate is in that medication. So you may have to do the volume of medication. Oops, my pen's going down. Volume of medication in milliliters times drop factor equals 60 times our time in hours. The 60, of course, is to convert hours into minutes, because if we're doing manually setting drops on an IV, it's going to be set in drops per minute. If you have a dosage that is given in mass, in milligrams, well, then the flow rate is going to be a dosage, the doctor's orders, D times the concentration over the time in hours. Same type of thing then applies if we're going to use a drip rate. it would be dosage times concentration times drop factor over 60 times the time in hours. Because once again, drops are going to be in drops per minute, not per hour. So you can see there's 5 formulas if you include the one from up above here that I threw at you very quickly. There's a lot of formulas to remember. I choose not to remember formulas and stick to the basic calculations. I'm going to show you a couple of other ways of doing these. We're going to see the dosage calculation formula, but I'm also going to show you how to use proportions. Proportions are a little bit easier because all you have to do in proportions is match up what units you have with what units you desire. The problem with proportions is you often need to use more than one. You need to repeat proportions. So you might have to use 2 or 3 proportions on one problem before you can get from what you're given to the answer. And then, of course, the third method, the last one I will show you at least, is dimensional analysis. And the nice thing about dimensional analysis is all you have to do is convert units. And it'll take you from where you start, what the information you're given, and just use the units to take you to where you want to go from there. Okay, so for today, we've got homework on a few pages. Pages 153 to 154. Problems 1 through 15. Pages 162 to 163. Problems 1 through 23. Let's just do the odds there. That's going to be kind of playing around with that dosage calculation formula. And page 168 to 169. 1 through 19, the odds. Those are going to be on the syringes, those last pages. The first page up here, like I said, is on the abbreviations, the medical abbreviations. You won't specifically be tested on those, but you'll need to be familiar with them enough to understand problems as we go. Okay, anybody have any questions? Okay, then, you guys have a great day, and we'll see you on Wednesday.